Hello everybody, I'm going to tell you about AGN powered by intermediate mass black holes, their scaling relations and growth. And I would encourage you to check out the presentations by my students Kirill and Victoria available at the conference website. The ultimate questions we're trying to answer are what are the SMBH seeds and how did they grow into supermassive black holes in the early universe? And local intermediate mass black holes can help if we assume that they evolve now similarly to high redshift counterparts. Of course, we have to start from the search for low redshift IMBH. And as many others, we do it by looking at optical spectra. What makes our IMBH search different from that by Greene and Ho 2004 and later? We start from a full sample of SDSS spectra without biases on galaxy luminosity, so we do not specifically look in dwarf galaxies. We also fit emission lines, narrow emission lines non-parametrically, and this gives better sensitivity for faint broad H-alpha components that we're after. And we use homogeneous data analysis for stellar populations provided in our RCSED catalog. You can check the website. The results published in our 2018 paper included 305 optically selected candidates with masses under 200,000 that of the Sun, and 10 of them were confirmed in X-ray. Most galaxies live in sparse environment. Supermassive black holes are thought to co-evolve with spheroids of their hosts and grow by mergers as suggested by the correlations between black hole mass and stellar velocity dispersion and bulges. However, a bulge can in fact be a pseudobulge growing in situ secularly. And black hole growth by accretion during the AGN phase will push it to higher black hole mass if the growth goes over time or extended period of time. The combination of the two factors might drag a BH back to the relation, and this is correlation versus causation. So if we preselect dwarf galaxies, we'll miss oversized pseudobulges. On the other hand, tidal stripping can reduce the bulge mass by orders of magnitude as in ultra-compact dwarfs, but would barely affect sigma, and this will push a black hole to a different direction. If accretion was the dominant SMBH growth channel at high redshift, then LISA will not likely see gravitational wave signals from IMBH mergers because they were rare. But on the other hand, Athena and Lynx will see signs of intense accretion in X-ray. We carried out follow-up observations on our candidates, and those went in using several different wavelength domains. So we expanded our X-ray sample with new XMM observations and by looking in the Chandra XMM and Swift archives. We populated MBH sigma relation by taking optical spectra with Magellan and SALT. The good quality spectra allowed to detect high-order Balmer lines and eliminate effects of dust or correct black hole mass estimates, and also to improve the black hole mass estimates thanks to higher resolution and depth. We also took infrared images and exceptionally good atmospheric seeing at Las Campanas and used archival HST data to complement the sample. What do we see? We see a lot of galaxies where black holes deviate from correlations toward higher masses of bulges or velocity dispersions of stars. And the strongest outliers are giant low surface brightness galaxies, which are the largest known disks in the universe that live in voids. Quite a few IMBH live in bar star-forming non-dwarf galaxies, and some of them are without evident bulges. As expected, tidally stripped systems are off the MBH and bulge relation on the top. We also found 8 examples of Eddington-limited IMBHs, which was quite a surprise because it's kind of 1/3 of the sample, and they have bolometric luminosity exceeding 40% that of Eddington. So if this period of fast growth goes for 100 to 300 million years, their mass can tenfold over this time. They also show some outflows in the O3 lines, but the feedback is probably too weak to affect star formation of their hosts. Conclusions. IMBHs in the nearby universe do not seem to co-evolve with their hosts, and they grow by accretion while their host grows secularly, even though the gas supplies might be connected. If the same happens at high redshift, then the super Eddington accretion is the dominant SMBH growth mechanism at low masses, and we expect to see high redshift IMBH and X-ray with the next generation space facilities. Thanks for your attention.